rates. Loading, the recording just started. Background tectonic loading rates in plate boundary zones tend to be on the order of up to maybe 100 kilopascal per year. And this is sort of the order of magnitude of the peak periodic stress variations by these different sources. So the background rate matters, but what also matters is the actual absolute strength of faults and the lithosphere and the stress that is being relieved by such earthquakes, so the stress drop, and that tends to be on the order of many megapascals, even up to hundreds of megapascal. Nonetheless, the idea that these very, very small stresses could modulate the occurrence of earthquakes kind of makes sense if you think about my little sketch here. If you have tectonic loadings, or you keep putting a straw on your camel's back every year, and then every year or every 12 hours you put a straw down and take it off again, you apply a seasonal stress, it kind of makes sense that earthquakes would be more likely to occur during the time when you had added that extra straw breaking the camel's back, right? So very small sources of stress. Why shouldn't it be possible that those affect the timing of earthquakes, at least in a statistical sense? So what I'd like to do is essentially look at two kind of case studies, two examples where we explored that. Act one is looking at the seasonal loading, deformation, and stressing, and maybe earthquake occurrence here in California. And then Act two is focusing on seismicity, specifically in the Parkfield region on the San Andreas fault, and looking mostly not at regular tectonic earthquakes, but these tremors or low-frequency earthquakes that have been discovered early in the millennium, deep on plate boundary fault subduction zones, as well as the San Andreas fault, and see what we can learn from these two different settings and range of periods that we consider. And so before I get into that, this is the little poll that we practiced a little bit earlier. So Roshan, do you want to also put the poll and see if that works? So if you get a poll, please try to answer that first question. Just what is your best guess as to which of these three statements is correct? As you might be able to tell, I'm an NPR fan. And so this is like the listener game in wait, don't tell me on Sunday morning, at least here in California. So quickly pick one of those three answers, and then we'll be excited to see what the right answer is. And if you know that show, it's usually one of the answers that you least think of. So that might be a good guess if you actually want to be right. Okay, I'll wait just a little bit longer. All right, do people need more time? I think about half have done it now. Let's do another 30 seconds. All right, I'll go to the next slide and then, oops. So, okay, why don't you publish or share the results of the poll? So we have about exactly half picked the second one, and then pretty much equal picked the first and the third one. All right, so here, that should be here. Can you see the result? Great.
Yeah.
Excellent. So why did we get into this? It was actually seeing some of these early CRACE results, CRACE gravity mission results that showed, albeit smooth across the state, given the low spatial resolution, a pattern of long-term decrease of water storage, mass at the surface of the Earth that gets captured by the time-dependent gravity measurements by the Crust satellite, superimposed by a seasonal variation of high amplitude related to seasonal variations in snow load, groundwater, and surface water. So we were curious, does this change in surface water and surface water storage, can it also be measured geodetically, which people have shown is possible on a global scale already quite some years ago. So starting in about 2006-07, the PBO GPS network, continuous GPS network, densified the number of continuously operating stations to a degree that we have lots of coverage and lots of redundant data. And so by the time we started to get interested in this, there was a large number of stations with many years of records that would allow for examining the long-term rate of surface deformation and any temporal variations such as those at a seasonal period. And so we'll look at two stations, two GPS stations, one here in the Eastern Central Valley and one here in the Southern Sierra Nevada, to look at, well, what does the vertical displacement of these stations look like? So the station in the valley shows this very rapid and very large subsidence by tens of centimeters with a modest seasonal cycle to it. And this we understand is being related to groundwater level troughs that produce a proelastic response, subsidence in response to groundwater level troughs. On the other hand, the station in the Sierra Nevada had a very, very modest, actually insignificant for the station, uplift rate during this time period, and shows stronger seasonal cycles and also some multi-year cycles that seem to relate to maybe periods of drought, the deep drought between 2012 and 2016, and also different variations of snow levels in the Sierras. So if you look at the aggregate time-dependent deformation of stations in the coastal ranges, so on either side of the San Andreas Fault, in the Central Valley, and in the Sierra Nevada, you can see sort of this dichotomy of behavior, uplift, slow but steady in the ranges surrounding the Central Valley, and net and very rapid subsidence with some seasonal deformation in the Central Valley. So the long-term velocities are shown here in the color scale. Blue is down, mostly in the Central Valley, but also in some other smaller sedimentary basin, and red is up. So the question is the uplift that we see surrounding the San Joaquin or Central Valley, is it tectonic, or is it actually related to this change in water load at the time scale of the observations? Similarly, the seasonal variations that we see in the ranges surrounding the Central Valley, are those also due to seasonal variations in surface load, seasonal variations in water storage? So to look at that, and you can see here on the seasonal pattern, I just added that line, you can see that the uplift in the valley coincides with subsidence in the ranges. And you can see that also in this diagram. So here, the size of the circles is the amplitude of the seasonal variation, the average seasonal amplitude. So the bigger the circle, the larger the seasonal variation. And the color is the phase, the time at which peak vertical position is observed. And you can see that in the Central Valley, the highest position is during the winter time, right? Kind of late what is that, February, March, and in the surrounding ranges, the peak uplift is in the late summer. So we have that anti-correlation of subsidence and uplift in the Central Valley, groundwater level dominated deformation, and in the surrounding ranges. So we know from well level observations and historical leveling measurements in the Central Valley that groundwater in the valley has been used unsustainably over 100 years, 150 years, due to agricultural use of water. So groundwater levels from the late 1800s to the late 1900s dropped by more than 100 meters in a few places. At the same time, that drop in groundwater level produced compaction of the sediments, storing that water, and produced subsidence at the surface of as much as 10 meters. This is kind of an iconic figure that you may have seen where Joseph Poland illustrates the amount of subsidence of the surface over the decades that his leveling measurements in the Central Valley documented. So we have tremendous loss of water and subsidence of the surface over that long time scale. So the total amount of water that was lost during this historical period is tremendous, and the subsidence that occurred is tremendous. Superimposed on this long-term groundwater level drop and subsidence are seasonal variations. Not surprisingly, we have seasonal precipitation and stream flow, and groundwater levels vary up and down by several meters with varying amplitude depending on where we look, if you look at these time series here. So to test if this change in surface load captured by well measurements and captured also by the Grace gravity measurements can explain, or how much of the surface deformation can explain, we use a simple 2D elastic load model, so just an analytical solution just to test, well, how do the observed long-term rates of vertical motion and how do the amplitude and phase of the seasonal motions compare with those that we would expect from a simple elastic surface load that is scaled or quantified by independent measurements of groundwater level and the Grace gravity data. And so that is shown here for the long-term rate. So this is a cross-section along this profile, southwest, northeast, across California. The open symbols are the GPS vertical velocities, and the diamonds show the predicted surface velocity due to 30 millimeters per year of equivalent water thickness, removal of water thickness load, just over the width of the Central Valley. So we simply do a 2D line load with a 60-kilometer profile located above the valley, remove 30 millimeters per year of water, and look at how fast surface points would uplift. And what you can see is, to first order, it matches the observed velocities really well. And you can see that the highest uplift rates are not in the high Sierra, where we have the highest topography. You might expect highest tectonic uplift rates, but they're right here in the foothills. So uplift rates actually increase towards the valley, as you would expect from this load model, and the amplitude of that surface vertical displacement is of the right order as that you would predict from independently constrained water storage changes. So that suggests that most all of the vertical velocities we see in California are due to water storage decrease, we don't need additional tectonic sources. They're difficult to differentiate from this. And if we take the long-term loss of groundwater in the Central Valley that we know from well data and extrapolate the uplift from this model, we easily get 10 centimeters of uplift of the Sierra Nevada over the last 150 years or so.
Can I ask a quick question?
Go ahead.
So in the model, it's just somehow loaded the surface, yeah? Do you assume anything about depth and how deep?
No, this is simply a surface load. Yeah, good question. It's simply a surface load on an elastic, not half space, but elastic substrate with uniform elastic properties. So really the simplest first order model. There's no, we did not try to apply that load, 200 meters down, right? The aquifers extend a little bit down. It wouldn't really make a difference because, right, the depth variation of that load relative to the width of the load is minimal. So the elastic load sigma wouldn't differ if we would try to place it in the subsurface, given the scale of the problem. But that's a good question. And this is definitely a very simple model. If we look at the seasonal behavior and do a similar model, but now we widen the load, we have a seasonal load actually load removal during the summer that is distributed from the coast ranges across the Sierras, because we have both groundwater, surface water, and snow making up much of that seasonal surface water storage. And you can see that the summer uplift that is shown by these red points, right? Those are the points that have their peak uplift during the late summer and fall, are roughly matched by the simple model of the seasonal amplitude of unloading of about 100 millimeters, which was the amplitude seen by the Grace model. The stations in the Central Valley that are not displacing because of elastic surface loads, but are displacing due to groundwater level changes and proelastic deformation, have a completely different pattern and much larger amplitudes. So we essentially have to separate out all the stations in basins that deform due to a completely different process, not due to elastic surface loads, but due to proelastic stresses that are due to groundwater volumes changing in the subsurface. Okay. Now this is obviously a very simple model. We can make a more detailed inversion of all the GPS surface time series. We're placing those on a spherical model with an elastic earth structure following the PREM model. And we're inverting for the time-dependent water storage that spatially varies as a function of time over the time period of our data. So here you can see now a movie of an estimate of water storage changes solely derived from the GPS time series. You can see the resolution is still limited by the spatial spacing of the GPS data, but this gives a nice model of what the variation of surface loads are. From that, we can calculate time-dependent stresses on faults of the San Andreas, the larger San Andreas fault system, including the Eastern California shear zone, using the USERF3 fault model of the earthquake-producing active faults in California. And you can see that normal stresses, shear stresses, and Coulomb stresses follow a very complicated cycle of seasonal stress variations, because the stress on any given fault depends not just on the overall loading, but it depends on your position relative to the load and your orientation with respect to the stress tensor that changes spatially and temporally related to that surface load model. So then there's that question, can we show if seismicity exposed to this complex spatiotemporally variable stress field responds in a substantial, significant way that we can document. If you just look at seismicity near Parkfield, right here, this would be a time series of Coulomb stress from our hydrological model. And then these are both the original catalog and declustered catalogs of seismicity in a circle around Parkfield right here. And you can see the average monthly month-of-year seismicity pattern here seems to have kind of a larger peak, broader peak in the fall, but then a second peak here in the spring. Our model only produces an average peak in the fall. So this spring peak, we don't have an easy explanation for. So this is just looking at one small area and seeing if there is something that looks compelling, that there is a cause and effect relationship. So there is periodicity at annual periods. There is a peak at the time of peak loading, but there's also a second peak that is not explained by this model. Now, if we look statewide, yep.
I have just a quick question. Just to follow better, so you use Fred's spherical harmonics model to basically put loads and calculate the elastic, the deformation, and fit the GPS data. So you were doing an inversion using the spherical harmonics model that he has, I think, something like that. And from that, you calculated the change of stress in the crust, and that's how you project it onto the fault, right? You calculate.
Correct.
All right. So that's.
Yeah, that's right. Now, both the deformation and the stresses, right, will depend on your choice of earth structure. There are also actually interesting possible viscoelastic effects, but this is just a simple layered, spherically layered elastic load and stressing model. Yeah. So this.
Hey, Professor, I have a question.
Go ahead. Yep.
So how long does it take for a fault to come back to its original state from the preloading to preloading state?
Yeah. Do you mean after it had an earthquake or just in general?
In this case, when it is the stresses because of the seasonal stresses. Yeah. Once it's loaded, how long it takes to come back?
So you have to think about this as being a temporal stress variation, right? Following these, what you can see in this example curve right here, superimposed on the background loading at anywhere up to maybe 0.1 megapascal per year. So it will come back to the same stress state every year, but it will eventually keep increasing, seeing increased load due to the background tectonic stress. And then at some point there will be failure, and it will start from, the beginning, right? And would need to build up stress again to be able to recur again. So it's a constant cycle of positive and negative stresses superimposed on a background loading rate. Does that answer your question?
Yes, in one of the graphs you were showing the months against the number of the earthquakes. So if you talk about, the third one. Yeah,
so this is taking all the earthquakes over the full time period here, and then just making a histogram of number of earthquakes per month of year. So we're essentially assuming that what is shown here can be simplified as a simple average annual cycle. So that is what is showing here for the model. So this is the average of the annual change from this model. And this is the corresponding number of earthquakes in January, February, etc.
Oh, okay, thanks.
Thank you. So given the complexity of the amplitude of stress variations spatially, normal and shear stresses, as well as the phase, different faults have peak loading, see a peak in loading stress encouraging failure at different times of the year suggests that just taking all the earthquakes in California and hoping to see a pattern is a flawed attempt, because we would be combining earthquakes in areas that we might expect to see more events in the summer, and earthquakes that occur in areas where the phase is different, right? Pretty much there is a fault somewhere in California that is expected to see higher loading at any time of the year. So that made us, rather than taking the full earthquake catalog, to focus as one way of getting at this on just the earthquakes for which we have focal mechanisms, and looking at the stress on the nodal planes of those events at the time when they occurred. So using the focal mechanisms, giving us knowledge about the geometry, one of the two nodal planes of a given event. And so here in red is shown events that occurred during positive Coulomb stress, and in blue those during negative Coulomb stress. So we can plot that in a diagram like this, where we have stress change, either shear stress or that is Coulomb stress or Coulomb stressing rate. And these are negative, so discouraging, and positive amplitudes. And then the x-axis is what we call a next value. This is the percentage of occurrence of events relative to the number that you would expect if earthquakes are completely randomly distributed. So positive next percentages or numbers mean that at a given stress condition, you had more events occurring than you would have expected if earthquakes are completely randomly distributed. And so what we find is that if we separate the catalog into strike slip and dip slip dominated events, we seem to be seeing as a correlation between stress conditions and rate of events, right? That excess or less than expected events for absolute stress. And for dip slip earthquakes, we don't really see anything here, but for stressing rate, so looking at the time at which stressing is at the highest rate preceding peak amplitude, we seem to be a correlation for dip slip earthquakes. So this indicates that maybe there's some interesting differences, frictionally speaking, between earthquakes of different faulting styles. If we look at large historical earthquakes, so going back in history only at events larger than 5.5 in California, where we don't have focal mechanisms, but we know which faults they were closest to. So we assume the geometry of the fault that this historical large event catalog closest to. We also see apparent correlation, maybe even more convincing, of shear stress and Coulomb stress, actually all the components in that sense. So it does look like large earthquakes and small earthquakes in California are being impacted, are modulated by seasonal stresses. And we can resolve that if we carefully examine their geometry in addition to their location and the spatiotemporal variations of the stress changes. So then in terms of our quiz, those of you who picked the first question were right. The second one just had it opposite to the pattern that we see. Stations in the San Joaquin Valley rise during the winter because of rising groundwater levels. And at the same time, the added water storage depresses the coast ranges in the Sierras. And that hydrological loading that we see is large enough to produce substantial uplift due to long-term loss of water in California, and also seems to modulate earthquakes. Okay, so that was Act 1. Do you have any more questions maybe on that before I move on to Act 2? Great. So now we'll focus on tidal modulation of seismicity near Parkfield, and I have a second poll to get you all interested in that topic. So here are 3 additional, I can, Roshan, can you put the poll up? So the first one is tremors in the deep crust. So tremors are occurring below 15, 16 kilometers in Parkfield. Are they essentially indistinguishable in their response to the tides as regular shallow earthquakes, tectonic earthquakes? Tremor rates in the lower crust can be modulated by really, really tiny shear stress changes, such as those that you get when you rub your hands really gently or at the bottom of a small creek, or C, tremors on the deep San Andreas fault cannot be triggered by clamping stresses. If I push across the fault, I won't get more tremors. So why don't you all pick one of those? And I'll go to the next slides while you find your answer. So tremor was first discovered deep on subduction zones, first in Japan by Obara, deep meaning 30, 40 kilometers below the known seismogenic zone, then in Cascadia, and then Bob Nadeau and David Durling discovered tremor also deep below the San Andreas fault near Parkfield, California. And so tremor, as you surely know, was a completely different kind of seismic signal rather than well-defined high-frequency dynamic slip events. This noise-like enduring seismic signal that people had to sort of completely reinvent methodologies on to be able to locate and study this signal. Okay, so it looks like the second one won, and then the first and the last one are sort of equal, a little bit less. Great. So we have this tremor here at Parkfield, and so we were curious about if tremors behave mechanically differently when they are exposed to these different types of periodic stresses. And here we focused in particular on tidal stresses. That tremor signal, with additional analysis and development of new methodologies, was recognized to be dominantly composed of tiny little low-frequency earthquakes that can be identified by defining templates and then using template matching, recognizing similar events that nominally have occurred in the same position. So David Shelley defined 88 families or source templates with which he was able to correlate hundreds of thousands of event occurrences over the years. So we have a catalog of, by now actually well over 1 million events of these low frequency earthquakes making up tremor below these nominally seismogenic zones. So these occur deep in the crust, below 15 kilometers, down to right near the depth of the manhole. So these occur at ambient overburden lithostatic stresses, normal stresses of hundreds of megapascal and temperatures of hundreds of degrees Celsius that we usually associate with being in the ductile regime of ductile flow in most crustal rocks. And so these low frequency earthquakes are highly spatiotemporally complex. They occur in varying combinations, bursts of activity of multiple families. After the Parkfield earthquake, as you can see here, they were accelerated. And so they make up this highly dynamic pattern of seismicity and fault slip that we understand these events to imply. So can we see any variation of occurrence of these in response to tidal stresses of very, very small amplitudes? So fault normal stresses, volumetric stresses, and fault normal stresses in general are much higher than shear stresses. So for the orientation of the San Andreas fault, the fault normal stresses are on the order of plus minus a few kilopascal. The shear stresses, right lateral shear stresses along the fault, are only of order of magnitude of 100 Pascal or so. So that in fact is about as low as the shear stress that I might apply when I rub my hands very gently or at the bottom of a stream. How about regular earthquakes? John Vidali published a paper in 1980 with colleagues, and what these plots show is similar to the plot I showed earlier, the distribution of events at the time of different stress levels, stress and stressing rate. And actually two curves here. The solid line shows the distribution you would expect if the events are distributed randomly in time, then you would see more events at very low stresses and fewer events at high stresses. So this is a probability density function of event occurrence. And same here for stressing rate. And you can essentially see the two lines don't differ, meaning the real catalog of about 13,000 earthquakes is statistically indistinguishable from a randomly drawn realization of earthquake occurrence, suggesting that tidal modulation is essentially non-existent. So here is the equivalent plot for normal stresses at the time of tidal occurrence. So here, expected is the background random distribution. This is the curve that you would expect if earthquakes are distributed completely randomly. And in red are those that were actually observed. And then here's the ratio of the two. This looks pretty random, but maybe some enhancement at higher peak normal stresses that you see right here that looks quite significantly above a ratio of 1, meaning no change. So this is for normal stress, which is the higher amplitude tidal stress. And here you see the result for shear stress. So now we're just looking at plus minus 100 Pascal. And you can see a systematic, really pronounced increase of event numbers above that expected for a random catalog at positive shear stresses, and a decrease, a lower rate than expected for a random catalog at negative stresses. And we look at the ratio, even just in these tiny increments of 20 Pascal, we can see a systematic enhancement of low frequency rates at times of positive shear stress. This is for all these 730,000 events. So I would say dramatic correlation with tidal shear stresses on the deep San Andreas fault in terms of the response of the low frequency earthquakes to the tidal stress cycles of just a few 100 Pascal. Now, given that we have so many earthquakes, we can repeat that exercise for all the different families. So now here you see the excess percentage for each family, simply taking the number of earthquakes during positive stress versus that is expected as from a random catalog. So here we have, in these red ones, we have 40 to 50% more events during times of positive shear stress. For these blue ones, that excess, that next value is only on the order of 10% or less for the shear stress. Okay, so we see a spatially variable pattern of that amplitude of shear stress modulation. And here's the pattern for normal stress. Remember, on average, we found that normal stress doesn't seem to have a strong correlation at all, except for maybe at the peak values. But when we look at that family by family, we do see that here in this northwestern part, just north of the town of Parkfield, we have correlation with tensile stresses. And here, just to the southeast of Parkfield, we see more event occurrences. We have a negative sign at times of clamping. So we actually do see apparent modulation of tremor in one place by tensile stress, unclamping, that's what we would expect, but also in another place by clamping stresses, positive clamping stresses. So what's special about that area and what's underlying this? That's a key question. Before I get to that, this shows if we take the apparent effective normal stress that is needed to produce this combination of high shear stress sensitivity and spatially variable, but overall lower normal stress sensitivity, and examining what kind of effective normal stress this implies, frictional stress this implies, we find that the effective normal stress has to be tiny. And if the effective normal stress has to be tiny, that's normal stress minus the fluid pressure, that means fluid pressure in the tremor-producing zone have to be nearly lithostatic. So only if fluid pressures are extremely high, able to even, exceed the least principal stress and produce nearly zero normal stresses can we explain this signal. We looked at, well, what kind of deformation process can drive this occurrence, and essentially ensured any ductile flow law of any mineralogy, quartz or serpentinite or more mafic minerals that we might expect are too strong to represent what the deformation in the fault zone surrounding these low frequency earthquake sources looks like. So this is a frictional system with very, very low differential stresses being needed to allow for that high sensitivity to tiny, tiny shear stress cycles. And I think we have still a bit of time. This is again the spatial pattern of shear stress versus normal stress sensitivity that I pointed out. And so we don't have a confident explanation of this, but we can point to a correlation of the zone of negative correlation with negative, meaning clamping normal stresses, being in a bend of the San Andreas fault that we can see both in the surface trace and in the location of the low frequency earthquakes. So we might be able to attribute this to the stress state near this fault bend zone and the distribution of fluid pressure in that system and the response of a fluid pressurized fault zone to these cycles of ambient tidal stresses. So this shows the strike of the fault with relation to that fault normal stress next number, that excess, showing these negative values right here in that zone. So overall, we think we can explain this extreme sensitivity to the tidal stresses of the San Andreas fault deep in the lower crust at temperatures and pressures of hundreds of MPa, hundreds of degrees Celsius, as being related to a zone that is fluid saturated and with fluids at extremely high pressures, meaning I would expect the fault zone to look something like this, where you have veining in the fault zone, meaning the fluid pressure can exceed the least principal stress. And that's consistent with seismic velocities being low along the fault zone, and they're also being based on resistivity data, apparent sources of fluids that might be available to produce the conditions for tremor here, similar to the conditions that we envision for tremor deep in subduction zones. So I think I will just quickly skip over the next couple slides. Essentially, we're starting to explore in more detail the period, the frequency, sensitivity of the tidal response related to the different constituents. So this shows a spectrum of tremor occurrence during the diurnal daily stress cycles, the semi-diurnal 12, 12.4 hour cycles. And we see variations in that suggest a frequency-dependent modulation of seismicity that we think we can relate to frictional, rate state frictional properties of the fault zone. And that again is spatially variable. This shows diurnal versus semi-diurnal modulation variation, their relative strength, and that seems to correlate with that pattern in the fault normal stress variation. So then the correct answer that most of you got was in fact that tremors, even though they're at these extremely high ambient stresses, because of high fluid pressure, they can be modulated by tiny, tiny shear stress changes, and less strongly so by normal stresses. And that apparent low frictional strength and low effective normal stress seems to provide conditions very different from regular earthquakes in the seismogenic zone. So just as an epilogue, you might wonder, well, what about the new Madrid seismic zone that you hold dearly, and you may well know the study by Tim Gregg and others, suggesting there's again a very strong seasonal variation of seismicity that can be related to seasonal variation of stress derived from surface load models, very similar to what I showed you for California. And we started to look at possible tidal modulation. And what we found was an apparent strong diurnal variation, but it looks like that diurnal, meaning 24-hour cycle, no 12-hour cycle, and we see only a very modest annual cycle, is probably dominated, I suspect, and I'd love to hear your thoughts, by lower magnitudes being affected by daily anthropogenic noise signals. But I'd be curious to know what you might suggest. Even though we look only at events larger than the magnitude of completeness, we still see these pronounced night-day cycles in the seismicity rate. And with that, I'll close. And if you have any more questions, I'd love to answer them. Thanks so much.
Thank you, Roland. That was a very informative, excellent talk. Yeah. I have a lot of questions with a lot of information there, so I'm trying to digest everything. I'm trying to go, so the tremor signal in Park field at depth, right? So you're arguing for pore pressures that are very close to lithostatic pressure. So what then is causing the seismic energy radiation? What are these tremor events? So it's not your typical, I guess, or maybe question, it's not the typical shear source double couple earthquake, right? It's something else that's radiating seismic energy.
So as best as we know, even though there are some competing models, they are shear slip events. So the model we have of these low frequency earthquakes are small slip surfaces contained in a dominantly aseismically shearing or slipping zone, and driven by both background tectonic loading as well as the seasonal or periodic variation. The increment of slip per event is tiny, 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 fractions of a millimeter. Their dimensions have been estimated by Amanda Thomas and Michael Bostock to be in the hundreds of meters, range, tiny stress drops, and their rate in places where we have good geodetic constraints, subduction zones, seems to be consistent with what you would expect from geodetic emergence. So we do interpret them as being similar to repeating earthquakes, right? Stick slipping patches in an otherwise aseismically creeping zone.
I see. So they're just these smallish kind of strong patches that are
And
okay.
just to add a little bit more detail, right? Based on sort of the pattern of occurrence, that each family might really be a cluster of patches, because we see bursts of events. We can see as many as 10 events during an episode of just like an hour or two. And we think that that kind of burst-like behavior, this, up to maybe a dozen of events during a very short time, is not repeated rupture of the same patch, but it's a whole family of neighboring patches going off in a very short time.
So then I think, so you said that the rate of these events is somehow strain rate dependent. So that, for example, the Parkfield events increase the strain rate on the aseismically moving fault, and then you have more of these small patches that are popping off.
Right. So during the Parkfield earthquake, just start that animation again. So if you watch, why is it not going? There we go. So when that zone, that tremor zone, gets loaded, and you see the Parkfield slick come up when that happens on the 28th. Stresses increase on that deep zone, and the rate of occurrence increases dramatically. So not only does the tremor zone respond to small tidal stresses, but also to static stresses from an earthquake in that, after slip kind of response, right? It is after slip in the deep lower crust.
Yeah, neat. Just one really quick question, and I'm sure the others have a ton of, but so what, why Parkfield you chose this area? Is that special, the San Andreas segment, or is it just because we have a lot of instrumentation there?
That's a great question. Parkfield was where tremor was first discovered, in large part probably because of the instrumentation, right? So we kind of thought, oh, we're going to start seeing that everywhere. And then Joan Gomberg found dynamically triggered tremor from the Denali earthquake in various places in California, on the Calaveras Fault, in the LA Basin, and many other places. We still haven't found ambient tremor anywhere else. So Parkfield is special, because we really should see tremor elsewhere if it's of similar amplitude. So the thinking is Parkfield might be special because below it you have a remnant of Farallon plate oceanic crust that may have provided the abundant fluids that are needed to produce the conditions that are more similar to those we see deep in subduction zones. So that kind of makes sense to me, that Parkfield might, in fact, in its environment, be different. But we did see trigger tremor in these other places. So maybe with even better analysis and instrumentation, we could find ambient tremor. At ANSA, people have looked for ambient tremor for a long time, and then it always turned out to be trains and other sources of noise. Still no confirmed detection of ambient tremor anywhere else.
I see. Thanks. Thank you.
So Roland, what is the fluid that's at lithostatic pressure at those temperatures?
Yeah, so I'm assuming they're the kind of fluids that we would find in fluid inclusions of rocks or in veins, at similar conditions, right? So they would be silicate-rich fluids that, if you precipitate them, could produce either depending on the surrounding lithology, could produce calcite veins, quartz veins, epidote veins. Just sort of thinking about it as a metamorphic petrologist. But it's hydrous fluids. Would be my guess. We would have to go down there and check if we want to know for sure. But that's what I would expect based on the depth and pressure and temperature conditions and lithologies involved.
And is do you attribute kind of the lower extent of the tremor sources having to do with something with composition or some other physical variable?
Yeah, that's a great question. We see these apparent spatial variations, right? And so there's sort of an overall depth dependent. We actually get more sensitive in the northern part, deeper on the fault. This is also where we're below the creeping segment, which starts here and extends up towards the north here. Then these spatial variations here in the normal stress sensitivity, we alluded to sensitivity to geometry of the fault, but there could also well be a lithologic contribution, right? Lithology would make for different structures, maybe different fluid compositions and properties. So we don't know. It's the important question to ask and try to resolve, but we don't know enough about the other factors that would allow us to attribute this to specific lithologies, etc.
Any idea on the hole in the middle there from 0 on the scale you've got now to 10?
Yeah,
Seems to be pretty constant.
good
And
question. And right, this is right below the center of the Parkfield earthquake rupture, whose aftershocks you can see right here. When you look at the temporal variation, like that animation that I showed you, right, of low frequency earthquake occurrence, these apparent bursts, they don't seem to want to jump across this. So it seems to be a real gap. I asked David Shelley, who produced the catalog, could there be just lower amplitude families there, right? Maybe due to, again, lithology or other differences. There's still slow slip and tremor, but we just weren't able to detect it. But we don't know. It's really suspicious. I keep asking people who do this kind of work, right? Autocorrelation and template matching. There should be many more families. David started out with just a handful of families when he started working on this here at Berkeley that he used as his initial templates, and then he was able to extend it to 88 that seemed to capture much of the tremor. But my guess is there may be hundreds more, right? But it would take a lot of effort to identify those. And maybe there are sources in between here that just haven't yet been identified and couldn't be used yet as templates for closing that gap.
if you go back to that, the video one or the animated one, that hole is both, it's before the earthquake and through the earthquake and afterwards. Is that correct?
Yeah, see, the hole stays, right? Because the templates are the same. So you're asking the right question. And I asked David exactly that. Did maybe the Parkfield earthquake, right, activate sources in that gap? And they were just not there, when during the time that was used to produce the templates, right? And so somebody like David himself or William Frank and a few others who have done this kind of analysis, should be able to check on that, right? Because we see similar things with repeating earthquakes. Both the Parkfield earthquake and also the Tohoku earthquake in Japan killed off some repeating earthquakes and birthed a few new ones in response to the earthquake occurrence. And it makes totally sense to me. We would see similar things for the low frequency earthquakes. And you know, mechanically speaking, in models of these kind of events in response to changing stress conditions, we also expect the emergence of dynamic sources due to those changes in conditions.
Yeah, thank you.
Mm-hmm.
Hey, Roland, I have a question. Do the changes in shear and normal stress you were showing from the in the first part of the talk, you were from the Central Valley modulation from the water, do these changes will affect also maybe a little bit less the southern, like more like Southern California, or they are too small?
Yeah, so right, we kind of cut it off here, you know, here, but you can see the amplitudes become lower in Southern California, and that makes sense because we're both the Central Valley and the Sierra Nevada end, so there's just less water storage and water storage variation. There is some, right? There, the transverse ranges, San Bernardino Mountains have snow, but it's just less. So the amplitudes are substantially less. Yeah.
And what about the Garlock fault? I was looking here.
So we didn't look specifically at the Garlock fault. The Garlock fault, you can see here, the stress amplitudes are not so high, right? But not that low. The thrust faults, right? The White Wolf fault, et cetera, have higher values. It doesn't have that much seismicity, so we didn't look specifically at, you know, is there evidence of time of year variations that's significant? Bill Holt and Young-Chung Kim, they looked at the Ridge Crest area using actually horizontal strains in GPS time series, and they argue that the seasonal loading in that area might have favored the earthquake to occur in the summer rather than in the winter. But if you just have an individual earthquake, it's really hard to make that argument, right? It's hard to make an argument that's statistically significant if you base it on single event occurrences of events that you care about because they're big.
Right.
Any more questions? I'll stop sharing.
Yeah, Ronald, so I have like simple question. So you have shown the GPS data and the subsidence rate, particular region. So if a region have influence on subsidence on upliftment, it could be due to the injection fluid. It could be due to the extraction of fluid from the subsurface, and it could be due to.
What was that last thing? Sorry.
Yeah, this is subsidence and upliftment. It could be a relation between the fluid extraction from subsurface, or like fluid injection from the surface to subsurface, or it could be the tectonic effect. So what could be the method to differentiate between that subsidence or upliftment is because of tectonic and that is because of the fluid stress difference?
Yeah, that's an important question. I mean, we went into this, I was interested in measuring vertical tectonics, right? Related to fault normal contraction across the coastal ranges, long-term dynamics, delamination below the Sierra Nevada, et cetera, et cetera. And then we found that most all of the signal could already be explained by the recent changes in surface water storage. I think it will just depend on being able to find, to quantify one enough that you can subtract it and then look at what's left over. You also mentioned injection, and in general, right, that groundwater and or injection related deformation, that's where you need to have independent knowledge of water level or injection activity so you can more directly correlate the deformation. Over the Central Valley, we also have INSAR data, so we can make out the subsidence signal in more detail and can relate it more directly to the locations of wells and their water level changes, so that we can do better in characterizing both of those processes. And that's really important to do. So I was kind of glossing over the need to try to recognize and separate out those different contributions.
Okay, thank you. So it's like we need to look up for the separate part individually to get the understanding. Okay, thank you so much.
Mm-hmm.
I think that's it. Thank you. Thank you, Dr. Roland, for your wonderful presentation, and thank you everyone for participating.
It's my pleasure. Thank you all again for coming, and enjoy the rest of your